Good morning, everyone. This is Sachin Chiske from Electrical Engineering Department, SND College of Engineering and Research Center. Today, we are going to start a frequency domain controller design. In the previous lecture, we discussed point related to time domain controller design. So, let us start about the point and preparation of this frequency domain controller and its design. So this frequency domain techniques together with the root locus method have been very popular classical method for both analysis and design of a control system, as they are still used extensively in industry for solving the controller design problem for many industrial processes and systems. Basically, they have to be included in academic curricula and modern textbook on control system. This chapter is organized as follows. In this section, we study the open and closed loop frequency transfer function and identify the frequency response parameters such as system frequency, bandwidth, then peak resonance and resonant frequency. In this section, we show how to read the phase and gain stability margin and the values of steady state error parameters that likes Kp, Kv and Ka from the corresponding frequency diagrams known as Bode diagram. This Bode diagram basically represents the magnitude and phase plot of the open loop transfer function with respect to the angular frequency omega. They can be obtained either analytically or experimentally. In this chapter, we present only the analytical study of Bode diagram, and through it should be mentioned that Bode diagram can be obtained from experimental measurements performed on a real physical system which is driven by a sinusoidal input with a broad range of frequencies. The controller design and techniques based on Bode diagram is considered in this section, and it is shown how to use the phase lag, phase lead and phase lag lead controllers such that the compensated system have the desired phase and gain stability margin and steady state error. It is also possible in some cases to improve the transient response since the damping ratio is proportional to the phase margin and the response rise time is inversely proportional to the system bandwidth. Also, in this section consists of a case study for a ship positioning control system, and in this section basically it represents a laboratory experiment. We comment on the discrete time controller design. Now, which are the basic objectives to study this frequency domain controller design? So the main objective of this is to show how to use this Bode diagram as a tool for controller design and such that compensated system have. First of all, the desired phase and gain stability margin and steady state error. These controllers based on the Bode diagram can also be used to improve some of the transient response parameters, but their design is so more complicated and far less accurate than the design of the corresponding controllers based on the root locus method. See this diagram. Basically, we are moving towards frequency response characteristics. Okay, so the open and closed loop system transfer function are defined already in our unit number 2. So for a feedback control system, these transfer functions are respectively given by, just like for the open loop transfer function, it is g of s into h of s, and for closed loop system, g of s upon 1 plus g of s into h of s, and that is equals to m of s. Here Fuji consists of m of s, whatever h of s also consider. Therefore, these frequency transfer functions are defined for sinusoidal input having all possible frequencies. That is, omega belongs to 0 to infinity or 0 to plus infinity, and they are obtained by one of the above equation, that is the transfer function for open loop and closed loop system, and by simplicity by putting s is equals to j omega, and therefore the transfer function for open loop system by putting s is equal to j omega is g of j omega into h of j omega. Similarly, put s is equals to j omega in closed loop transfer function, so we get g of j omega on numerator side upon 1 plus g of j omega into h of j omega. So by using the frequency transfer function in the system analysis gives complete information about the system steady state behavior, but not about the system transfer response. That is why the controller design techniques based on frequency transfer function improve primarily the frequency domain specifications such as phase and gain, relativity, stability margin, and steady state error. However, some frequency domain specifications to be defined soon can be related to the certain time domain function. For example, the wider the system bandwidth, the faster the system response, which implies a shorter response rise time. See this diagram. For the magnitude and phase of the open loop frequency transfer function, one is able to read directly the phase and gain stability margin and corresponding phase and gain crossover frequency. So in this section where we present the Bode diagram, which is also represent the magnitude and phase plot of the open loop frequency transfer function with respect to frequency, with magnitude being calculated in decibel, that is dB. We will show how to read this value for Kp, Kv, and Ka. In addition to the phase and gain margin obtained from the open loop frequency transfer function, these other frequency response parameters can be obtained from the frequency plot of the magnitude of the open loop frequency transfer function. This plot is given in the next figure, series diagram, and the main closed loop frequency response parameter are system bandwidth, peak resonance, the resonance frequency, and they are formally defined below. What is system bandwidth? So this represents the frequency range in which the magnitude of the closed loop frequency transfer function drops no more than 3 dB, that is 3 decibel from its zero frequency value. The system bandwidth can be obtained from the next equality, which indicates the attenuation of 3 decibel as m of j omega h omega is equals to 1 upon root 2 into m of 0 is equals to omega bw. It happens to be a computationally very involved to solve the above equation, that equation I did here, for higher order system, and hence the system bandwidth is mostly determined experimentally. For second order system, the frequency bandwidth can be found analytically. Now we are moving towards the peak resonance. This is obtained, or this peak resonance is obtained by finding the maximum of the function m of j omega with respect to frequency omega. It is interesting to point out that the system having a large maximum overture and also large peak resonance. This is analytically justified for a second order system in problem. So this resonance frequency, this is the frequency at which the peak resonance occurs, and it can be obtained from dd omega of mj omega is equals to 0, and that is equals to omega. Now we are moving towards Bode diagram, or the equation which represents basically the Bode diagram. Wait for a minute. So these Bode diagram are the main tools for frequency domain controller design, a topic that will be presented in details in this section. And in this section, we show how to plot these diagrams and how to read from them certain control system characteristics, such as the phase and gain stability margin and the constant required to determine the steady state error. This Bode diagram basically represents the frequency plot of magnitude and phase of the open loop frequency transfer function, that is g of j omega into h of j omega, and the magnitude is plotted in dB, that is decibel, on the log of omega scale. So in general, this open loop frequency transfer function contains elementary frequency transfer function representing a constant term, that is static gain, and dynamic element like system real poles and zeros and complex conjugate poles and zeros. So we first study independently the magnitude and frequency plot of each of these elementary. This frequency transfer function, since the open loop frequency function is g of j omega into h of j omega, is given in terms of the product and ratio of elementary transfer function. It is easy to see that the phase of g of j omega into h of j omega is obtained by summing and subtracting phases of the elementary transfer function. So also by expressing the magnitude of the open loop transfer function in decibel. The magnitude g of j omega into h of j omega is obtained by adding the magnitude of the elementary frequency transfer function. For example, here g of j omega into h of j omega decibel is equals to 20 log of, in numerator, k into j omega plus z1 and j omega plus z2 in numerator, and in denominator it is j omega into j omega plus p2 and j omega plus p3 in denominator side. All are having the base 10. So it is equals to 20 log of mod of k plus 20 log of j omega plus z1 plus 20 log of j omega plus z2 plus 20 log of 1 by j omega plus 20 log of 1 by j omega plus p2 plus 20 log of 1 by j omega plus p3. Here also every term is having log of to the base 10, and argument of j omega h of j omega is equal to argument of k plus argument of j omega plus z1 plus argument of j omega plus z2 minus argument of j omega minus argument of j omega plus p2 minus argument of j omega plus p3. So in this following, we show how to draw this Bode diagram for elementary transfer function or frequency elementary transfer function. So here the constant term are k is equals to 20 log of k to the base 10, and it is in decibel. So what is the value of k we can be find? So it is positive number for k greater than or equals to 1, sorry, k only greater than 1, and negative number for k is less than 1. So argument of k is equals to 0 degree for k is greater than 0, and it is minus 180 degree for k is less than 0. So the magnitude and phase of this element are easily drawn and represented in following figure. Consider here x-axis, that is omega, log of omega, and it is 0 reference line, and second y-axis can be considered as mod of k in dB, and in second diagram it is shown as angle of k. So for the first case, that is value of k is equals to positive number. Yes, definitely k is greater than 1, and it is shown above the 0. Consider this first line. If value of k is less than 1, then it shows a negative number. It is clearly identified. Now for argument of value of k is equals to 0 degree. So definitely this 0 degree can be lie on the 0 reference line when k is greater than 0. And when value of k is less than 0, then it is minus 180 degrees. So it is shown on the negative side of the second diagram. Say properly this diagram. And it has pure integrator. So the term transfer function of the pure integrator is given by, or it has the following magnitude and phase, that is g of j omega in decibel is equals to 20 log of 1 by omega, and that is equals to minus 20 log of omega to the base 10, and argument of j omega is equals to minus 90 degrees. So it can be easily proved, or it can be easily observed, that this phase for a pure integrator is constant, whereas the magnitude is represented by a straight line intersecting the frequency axis at omega is equals to 1 and having the slope of minus 20 dB per decade. Both these diagrams are represented in the following figure. Thus, a pure integrator introduces a phase shape of minus 90 degree and again attenuation of minus 20 dB per decade. Now, what is pure differentiator? The transfer function of a pure differentiator is given by g of j omega is equal to it is general g of j omega and it is j omega. So its magnitude and phase are easily obtained as g of j omega decibel is equal to 20 log of omega to the base 10 and argument of g of j omega is equal to 90 degree. So the corresponding frequency diagram are presented and it can be concluded that a pure differentiator introduces a positive phase shift of 90 degree and an amplification of 20 decibel per decade. So what is the real pole? The transfer function of a real pole is given by g of j omega is equal to p upon p plus j omega and that is equal to 1 upon 1 plus j omega by p and it has the following magnitude and phase. So this g of j omega is equals to minus 20 log of 1 plus omega by p to the power 2 to the power 1 by 2 to the base 10 and argument of g of j omega is equal to minus tan inverse of omega by p. So this phase diagram for a real pole can be plotted directly and it can be seen that for large values omega and omega is greater than or greater than equals to p and this phase distribution is minus 90 degree. So for the omega is small so that the omega is less than or p the phase is close to 0 and for omega is equals to p the phase contribution is minus 45 degree. This information is sufficient to sketch the argument of j omega as given in figure. So for a magnitude, we see that for a small omega, the magnitude is very close to 0. But for the large value of omega, we can neglect 1 compared to omega upon p so that we have a similar result as for a pure integrator. That is, we obtain an attenuation of 20 dB per decade. For small and large frequencies, we have a straight line approximation. The straight line intersect at omega is equal to p, which is also known as a corner frequency. The actual magnitude curve is below the straight line approximation and it has a biggest deviation from the asymptotes at the corner frequency. Similarly, what is the real zero? This transfer function of the EMA representing a real zero is given by g of j omega is equal to 1 by z in bracket z plus j omega is equal to 1 plus j of omega z. By using this analysis similar to that performed for a real pole, we can conclude that for small frequency an asymptote for the magnitude is equals to 0 and for large frequency the magnitude asymptote has a slope of 20 dB per decade and intersects the real axis at omega is equals to z, that is corner frequency. The phase diagram for small frequencies also has an asymptote equals to 0 and for large frequency an asymptote of 90 degree. So the magnitude and phase Bode diagram for real axis element are represented in this figure. Now, moving towards the complex conjugate poles, the transfer function of an element representing a pair of complex conjugate poles is in fact a transfer function of second order system. So, phase and gauge margin stability from Bode diagram indicates how to read the phase and gain stability margin from the frequency magnitude and phase plot of the open loop feedback transfer function. In this